Hey everybody, today's video is going to be about something called a counterexample, which is a concept that everyone has engaged with before, and I'm just going to speak sort of more about what it is and why it's something that humans find it so difficult to use properly. So to start off with, I'm going to give a little puzzle, and after I give the puzzle, maybe pause and think about your answer, because this is a puzzle that a lot of people get wrong. It's called the Watson selection task, and it's quite straightforward. The idea is that there are 4 cards, and on every card, one side has a number and the other side has a letter. And there is a rule. And the rule says if a card has a vowel on one side, there is an even number on the other. Right, so a pretty straightforward rule. And the question is, if you just see these 4 cards with these 4 sides, what cards do you have to flip over in order to make sure the rule is being followed? So what cards need to be flipped to demonstrate that this rule is definitely true for all the cards? So yeah, feel free to pause here and have a think about it. I'm going to get into the answer now. So I'll start with the most common wrong answer. A lot of people say, well, the question is about vowels and even numbers. So it feels very intuitive that you would just say, I'm going to check A and 4. I'll flip those over, and as long as they fit the rule, then the rule has been followed, and I shouldn't really care about B or 7 because they're not part of the statement. These aren't vowels and they're not even. Now this is wrong, and it's very wrong, and I'll explain why. So picking A is correct. Alright, the claim says that if a card has a vowel on one side, there is an even number on the other. So obviously, if A didn't have an even number on the other, like it was an 8 or something, sorry, if it was like a 7 or something, that would violate the rule, right? So I have to flip over A to make sure the other number is even, because if it isn't, the rule is broken. Now, this is actually the second most common wrong answer to just pick A. A is one of the valid cards, but there's one other card. I'll start with why 4 is not correct. The reason why 4 is not correct is because, well, think about it. What else could be on the other side of the 4 card? Either a vowel or a non-vowel, which is a consonant. If the thing on the other side of the 4 card was a vowel, that's fine, right? The rule still works. If a card has a vowel on one side, there is an even number on the other, cool, it's valid. If the letter on the other side of the 4 is a consonant, like C, well, that's fine too. The rule hasn't been violated. Remember, the rule says if a card has a vowel on one side, the other side is even. So if this card has a consonant on the other side, well, then it doesn't even matter that it's a 4. So either way, we actually don't care what's on the other side of this card, because either way, this rule can't be violated. The answer for the other card you should be checking is 7. And I'll explain why. Because what's on the other side of 7 actually does pertain to the rule. Because if what's on the other side of 7 is a vowel, then this card will break the rule. It will disprove the rule. If the thing on the other side is an E, then we now have a card with a vowel on one side with a non-even on the other. And that's the answer. So the answers are you should check cards A and 7. If you got that correct, then well done. I think when people get given this question without knowing that it's a counterexample style question, they often get it wrong. Most people will pick A and 4 without thinking much about it. So I'm going to start with another intuition for why the answers are A and 7. And then I'm going to talk more about why a lot of people get this question wrong. So we can represent 4 different combinations of cards, right? There are 4 different cards really that can exist in this problem. And the reason there's 4 different cards is because there's 2 categories of things on either side, which creates 4 options. So let's just talk about this category. So I'm going to say it can either be a vowel or a consonant. I'm just going to say V or C. And it can be even or odd, right? And I can draw a little table here. And inside this table are going to be my 4 options. It's going to be a vowel, an even vowel, odd vowel, even consonant, odd consonant. And I'm going to write down what these cards actually happen to say behind the column that pertains to them. So A is a vowel, it's going to go here. B is a consonant, it's going to go here. 4 is our even number, so we'll go here. 7 is our odd number, so we'll go here. So what the rule is saying is that if a card has a vowel on one side, there is an even number on the other. Which means that if it's a consonant, it doesn't matter. Both of these cases are going to be okay. They're not going to disprove the rule. There's a val on one side, it has to be an even, which means that this is fine. In the same way that these two are fine. But this is what we need to disprove. We need to make sure that there's no card that has a val and an odd number. This is the only way that my claim will be proven false. So it follows that I have to only check cards that may pertain to this column, which is card A and card 7. That's why 4 and B are irrelevant to me. Now, interestingly, there are other ways that you can phrase this problem that make the question a lot more obvious. So for example, there's a variation called the bar variation, where instead of numbers and vowels, instead of numbers and letters, the cards refer to people who are in a bar and what they're drinking. So on one side is going to be the age of the person, and on the other side is going to be the drink that they're drinking. Let's say the 4 cards now are age 12, age 32, we'll say beer, and we will say, for the other one, we'll say something non-alcoholic. So we're going to say Coke, like, Coca-Cola. Sorry about the writing. And now let's say you're a police officer and you've entered into the bar and you need to figure out you need to make sure that no one's underage drinking. All right, make sure nobody's underage drinking. Underage drinking is really bad. So, gotta make sure that's not happening. Now what cards do you flip over? Now it becomes very, very obvious what the answer is, right? The question is about underage drinking. So we don't care what the 32-year-old's drinking. So we don't need to flip his card over. We don't care who's drinking Coke because the kids can drink Coke and so can the adults. We do care who's drinking the beer. So we need to investigate this because that might be a kid. And we care what the 12-year-old is drinking because the 12-year-old is drinking something like beer. That is bad. Now this is the exact same question, but phrased in a different way. And when people are asked it in this variation, the answer becomes a lot more obvious, which I think is kind of interesting. Some social theorists say that the reason is because this is about a rule that pertains less to, common life, and it's not really a moral rule. It's not like a socially enforced rule that cards have a vowel on one side can't have an even number on the other. It's very arbitrary. This isn't the sort of rule you'll see in nature or in general life. But this rule, the rule that's being violated here, is a social rule. And some theorists say that when there's a social rule, we think like this more perfectly. We're better at coming up with counterexamples. I guess because we're more worried. It's, any cop will immediately think, who's drinking the beer? But it wasn't as easy to see that you have to flip the 7 instead of flipping that 4. Cool, so the basic idea here is that everyone knows to flip the A, but a lot of people think to flip the 4. And it's because of something called a counterexample, which is something that's very hard to find. Before I get more into what a counterexample actually is, I'm just going to give one more example of a game. Now this is a game that we can't actually play because it's 2-player, but I'll describe how the game works. There's a YouTuber, Veritasium, who did a really good video about this, which is where I learned it. I don't know what it's called. Let's just call it the 3-digit game. And here's how it works. I'm thinking of a rule, and that rule validates some 3-digit combos and invalidates others. So for example, my rule might be they all have to be even, or they all have to be odd, or the 3-digit number has to be prime. I'm thinking of a rule. And let's say actually, instead of 3 digits, let's just say it's 3 numbers. I'll give us more leeway. A 3-number game. So you can propose any 3 numbers. We're going to say they have to be natural, so no pies and no 3.4s, anything like this is not allowed. Whole numbers. And I say to you that 2, 4, 8 fits my rule. That's all I say to you. And now the game is that you get to keep proposing 3-number combinations to me, and then I'm just going to tell you whether or not they fit my rule. Alright, so 2, 4, 8 fits the rule. And then you propose another example, and I'll tell you if it's the rule or not. Remember, your goal is to figure out what the rule is. So let's say that you propose, and this is a very common second proposal, you propose 4, 8, 16. And then I say to you, fits my rule. And now you're thinking something, you've discovered something. It's like, oh, well, these are doubling and these are doubling. So it's very reasonable to then propose something like, what about 3, 6, 12? And then I say to you, does that fit my rule? I say yes. And now you're pretty confident, things are doubling. Let's do another one for safe measure. Let's propose 1, 2, 3. And I say to you, that fits my rule. Now, at around this point, a lot of players will very confidently say, I figured out the rule. The rule is the numbers are doubling. That's wrong, right? That isn't the rule. And what's interesting is that even when you tell people that this isn't the rule, they sort of get frustrated because it's like, well, what do you mean? I've given you 4 examples. They all fit the rule. This has to be the rule, right? And I'll tell you what the actual rule was. The rule is that the numbers are just always increasing. So technically all the doubling numbers also work. But what I'm getting at is that when a human has a intuition for what the answer is going to be, they're only going to propose combinations that would work if they were right. They like seeing this tick. It feels good to be told that you're correct. And this is what's known as a confirmation bias, which I'll speak more about. But if you're really playing this game as a mathematician and your goal is to figure out the rule as fast as possible, the first thing you should do is propose something that wouldn't be right and look for the X. That's called a counterexample. And often counterexamples will give you way better information. So let's say I'm at this point here and I'm thinking it's doubling. And instead of being very, very confident that the numbers are doubling, I'll just pick something that isn't doubling. I'll pick something like, let's just change it a bit. Let's go 4, 7, 16. And I get an X. What I'm getting at is that this guess here gave me way more information than just guesses that validate what I already think. And this is what a counterexample is. And humans, when they play this game, are really, really bad at it. And in fact, when you tell them that this isn't the rule, that it's not just doubling, they actually might even get defensive or think it's a prank. They're like, what do you mean? Are you doing a bit? Because everything I've guessed was valid and they were all doubling. If you think something's true, try and prove it wrong. And if you can't prove it wrong, it's way more evidence that it's true than just one example of it being true. And this is something we do a lot of math. So finding these counterexamples are unintuitive, and there's kind of a evolutionary explanation for this, I believe. A lot of people in science and in math, I think, like to believe that logic is something that we evolved to do. Through evolution, the smarter animals, the more logical animals will survive. And so as a species, we've been getting more and more logical, and that this is a skill that we've developed to analyze the logical world. But it follows then that if it's just evolutionary, that there are some biases that are probably actually good to have from an evolutionary point of view. For example, the confirmation bias, which is just a bias that says if you think something's true, you're going to look for more evidence that it's true because you want it to be true, right? We love things to be true. Which means you won't look for these counterexamples. There's a really good example of something that might not be true, but is an evolutionary benefit to believe in this. And this is to do with something called a negativity bias. The idea is that if you're a caveman, and I'll give the caveman a little bat like this, and there's some bushes here, and the bushes are like rustling a little bit, right? And the caveman thinks that it's a tiger. If the caveman always thinks to himself, that's a tiger, that's actually pretty beneficial because sometimes it will be a tiger. Even if most of the time, even if 80% of the time it's just the wind, right? It's useful for this person to believe that it's a tiger because then he'll run away every time. And the 20% of times that it actually is a tiger, or even the 1% of the time it is a tiger, his life will be saved. And I think this is why we like to create boogeymen a lot as a society. There's a lot of things that we're really, really skeptical of. And it's because sometimes the thing's actually there. But we have a bias because this caveman has to believe there's a tiger there. Because if he didn't believe there was a tiger there, he would be more likely to be eaten. Even if most of the time this belief is incorrect. if I was to take two claims and just say P and Q, right? And I said if P, then Q. If P, then Q. We can make these whatever we want. So let's say the classic example is P means it's raining and Q means I'm going to bring an umbrella. So this statement says if it's raining, then I'm going to bring an umbrella. There's a law of logic, and it's called modulus ponens, and I won't write that down. But modulus ponens says that if P implies Q, and this is the way we write that in math, if P implies Q, and I'll just write it, if P implies Q and P, then Q. This is the rule that everyone's really comfortable with, that we use all the time because it's affirmative. We're saying, if it's raining, then I'm going to bring an umbrella, and it's raining, therefore I'm going to bring an umbrella. This is almost like an axiom. We don't even need to really explain why this is true. This just feels so self-evident. Now, modulus ponens, which is very self-explanatory, has a cousin called modulus tollens, and this one's a lot less self-evident. This one says that if P implies Q and not Q, then not P. And what we find is that these two statements are both equally valid. And the analogy for this one would be like, if it's raining, I've got to bring an umbrella, and I didn't bring an umbrella, therefore it didn't rain. This lends itself more to this idea of finding a counterexample. If P implies Q at every situation, but I can find an example where Q won't be true, then P didn't imply it. This is kind of like why we had to check the 4 card instead of the 7 card. Because the rule just was, for that game we did earlier, I'm just going to write a vowel implies an even. So if a vowel implies an even and there's a vowel, then there must be an even. But the true way of flipping this claim around will be if not even, then not vowel. Another way of writing this is if there's an odd number, the other side has to be consonant. And that's a counterexample. One more thought I had about counterexamples before I end this video is that there is sort of a political application to this bias. There's a lot of speak now in politics, especially online, about things called echo chambers, which you might have heard of. An echo chamber. The idea is that, let's say you're online and there's a couple of groups online. These things believe thing A, or these people believe thing A, these people believe thing B. And you're like, there's people in the middle, but most people firmly believe thing A or thing B. And the idea is like a polarizing effect. If you're this person here, and you kind of believe thing B, you're sort of on team B, but you don't know enough, because you already are a bit more susceptible to ideas about thing B, when these people talk, you're going to listen a little bit more because you've got a bias towards thing B, your confirmation bias. And thing A is going to feel a bit more distant to you. And so over time, what's going to happen is you're slowly going to move to thing B over and over again. And this is kind of what it means to be like radicalized online. And now when you're so firmly in the thing B camp, you're not even thinking about thing A. These people are like gone. You're not engaging with this media anymore. Your algorithms don't show you things from thing A. And now every time someone says something about thing B, you're going to keep listening and it's going to keep reinforcing you. I think the reason they call it an echo chamber is because when these people also have the same belief, the idea is that it's echoing, it will bounce back off the walls, and these people are only hearing other people who say things they already think. And when that happens, people get more and more extreme. This idea of not being able to find counterexamples, I think, can apply a lot to conspiratorial thinking. I don't want to give an example of a conspiracy for this, because I don't want to give any proper takes about that. But a lot of conspiracy theories will take the form of like there's an evil shadow government or an evil group of people, and they're evil, objectively evil, whatever, and they do bad stuff to the people. So you've got all the people here, and the evil people doing bad stuff. And it's really hard to talk to a conspiratorial person because what they believe is really, really easy to think. Because there's no real way to give a counterexample, right? What sort of counterexample will you give? I mean, you can give an example of something good that this guy has, and therefore the evil people might have not, didn't give them a bad thing, right? But then they're just going to say something about how, oh, that's what they want you to think, or they're doing this is a political release valve. They're keeping me just as happy as I can, And it's like, I suppose that's true. If you were trying to keep your evilness a secret as like a shadow government, you wouldn't want to be like 100% evil. You'd want to be a little bit good. But now here's a problem. Their claim about the evil shadow people cannot be disproven. Because every time a bad thing happens, it's proof because the evil people do bad stuff. And every time a good thing happens, the easy out is that, well, the evil people are going to do some good stuff to you to, hide the bad stuff. I don't like engaging with ideas like this because you can't even debate them because there is no counterexample that you can even find. One really good question to ask if you're debating someone, especially if they think conspiratorially, and this question can break people's brains. This is not something people are familiar with being asked. That question is, what sort of evidence would you need to change your mind, or to have your mind changed? Because remember, they think that P implies Q. So ask them, what sort of evidence would you need to have your mind changed? Basically, if I can prove that Q hasn't happened, then P can't have happened. This is my counterexample. Especially when someone's really into the online conspiratorial space, this question can really make them uncomfortable. Because it's like, yeah, it makes sense. You should be able to have your mind changed. Otherwise, their belief has no point. Alright, that's the end of the video. My basic thesis here is that if you think something's true, don't just think about what reasons it's true. Think, if I really hated this belief, or if I was a critic, how would I prove it false? And if you try and prove something false and you fail, that's way more evidence that that thing is true. And we've done this a lot on this channel, obviously, with the math stuff. Cool. Alright, that's the end of the video. Cheers, guys.